Imagine a substance so potent, so enduring, that it remains lethally dangerous for thousands of years. It's hot to the touch, radiating an invisible menace. This is nuclear waste, the byproduct of our atomic age, and it presents one of humanity's most profound and persistent challenges. It's a material that defies easy disposal, a silent, simmering threat that outlives civilizations. For generations, we've grappled with its existence, searching for a solution to its eternal presence. The question inevitably arises, a seemingly elegant answer to an intractable problem. Why don't we just blast it into space? Why not launch this dangerous legacy far beyond our world, into the cold, indifferent void? The idea holds a powerful, almost irresistible appeal. Picture it, a rocket, laden with the very essence of our nuclear dilemma, ascending into the heavens. It would carry the waste far away, beyond Earth's atmosphere, beyond its gravitational pull. The perceived benefit is clear, out of sight, out of mind. No more harm to anyone on Earth, no more contamination of our precious ecosystems. It sounds like the ultimate clean solution, a final, definitive answer to a problem that has haunted us for decades. The concept is simple, almost poetic in its ambition. Send it to the sun, or deep into interstellar space, and Earth would be free. But the reality, as with so many grand solutions, is far more complex. It's not that simple. The dream of space disposal quickly collides with a harsh, undeniable truth. Rockets fail. The history of space exploration, while filled with triumphs, is also punctuated by catastrophic failures. Each launch is an intricate dance of immense power and delicate engineering. A rocket carrying nuclear waste is not just a payload, it's a ticking time bomb. A catastrophic explosion, even on the launch pad or in the lower atmosphere, would unleash a nightmare scenario. Think of the Challenger disaster, a moment etched into collective memory. Now imagine that explosion, but instead of just debris, it's tons of highly radioactive material. The implications are terrifying. Such an event would not merely scatter fragments, it would aerosolize radioactive particles. The potential for widespread contamination, carried by winds and deposited across vast regions, is a chilling prospect. To grasp the true horror of such a failure, we need only look to the past. The Chernobyl disaster, a nuclear meltdown on Earth, offers a stark, terrifying preview. It was a localized event, yet its impact was global. Chernobyl released massive amounts of radiation, contaminating an area larger than many countries. It forced the permanent evacuation of hundreds of thousands, creating an exclusion zone that remains largely uninhabitable. The long-term health problems, the environmental devastation, the sheer human cost, these are the enduring legacies of Chernobyl. Now, consider a space launch failure. Instead of a single reactor core, imagine multiple tons of highly enriched, highly radioactive waste exploding high above the Earth. The radiation would not be confined to a region. It would be dispersed across continents, carried by atmospheric currents. The scale of contamination would be unprecedented, dwarfing even Chernobyl. It would be a devastating, irreversible catastrophe, rendering vast swathes of our planet uninhabitable for generations. Even if we could guarantee perfect launches, the cost of sending nuclear waste into space would be astronomical. We are not talking about a few isolated shipments. The sheer volume of nuclear waste generated globally is enormous. Every nuclear power plant, every medical facility using radioactive isotopes, every research institution, they all contribute to this ever-growing inventory. To launch it all would require a constant, unending stream of rocket launches. The cost of building these rockets, the infrastructure for safe handling and loading, the rigorous safety protocols required for each launch, it would be an economic burden beyond comprehension. It would drain resources that could be better spent on developing safer, more sustainable solutions here on Earth. The financial implications alone make space disposal an impractical fantasy. It is a solution that would bankrupt nations long before it solved the problem. Even if a rocket successfully cleared Earth's atmosphere, the problem doesn't end there. Where exactly would the waste go? The options are fraught with their own perils. Sending it to the sun sounds appealing, a fiery end to a dangerous substance. But reaching the sun requires immense precision and energy, far more than simply escaping Earth's gravity. It would demand a trajectory so exact, so powerful, that the slightest miscalculation could send the waste hurtling back towards Earth. The alternative, sending it into deep space, presents another set of challenges. What if the trajectory is off? What if it drifts into an orbital path that eventually intersects with Earth, or another celestial body? The universe is vast, but our control over objects within it is still limited. And then there's the terrifying possibility of re-entry. If a rocket fails to achieve its intended escape velocity, or if its trajectory is compromised, the waste could re-enter Earth's atmosphere. The friction of re-entry would cause it to burn up, spreading radioactive particles across the globe. This is not disposal. It is global contamination by design. The problem of where to put it, even in space, remains a profound and dangerous unknown. Given these insurmountable obstacles, humanity has focused its efforts on managing nuclear waste here on Earth. The current approach, while not without its own challenges, is safe storage. This involves isolating the waste in robust, shielded containers, often submerged in water or encased in concrete. These interim solutions buy us time, but they are not permanent. The long-term solution, widely accepted by the scientific community, involves deep geological repositories. These are facilities designed to store nuclear waste thousands of feet underground in stable rock formations for tens of thousands of years. Places like Yucca Mountain in the United States, though politically contentious, represent the scientific consensus for long-term isolation. The goal is to place the waste in a location where natural geological processes will keep it isolated from the biosphere until its radioactivity has decayed to safe levels. Beyond storage, ongoing research explores advanced reprocessing techniques. This involves chemically separating useful components from the waste, potentially reducing its volume and radioactivity, and even creating new fuel. While reprocessing has its own complexities and proliferation risks, it offers a path towards minimizing the waste burden and potentially extracting more energy from existing nuclear materials. These Earth-based solutions, though imperfect, are grounded in scientific reality and risk mitigation. The idea of shooting nuclear waste into space, while tempting in its simplicity, is a dangerous illusion. It seems like a quick fix, a way to banish our problems to the stars, but the reality is far more grim. The risks are simply too high. The potential for catastrophic launch failures, leading to widespread radioactive contamination, is an unacceptable gamble with the future of our planet. The costs are too great. The financial burden of such an endeavor would be crippling, diverting resources from more viable and responsible solutions. The potential for disaster is not merely theoretical. It is a terrifying certainty given the inherent dangers of rocket science and radioactive materials. We cannot afford to make such a monumental mistake. We must confront the reality that nuclear waste is our responsibility here on Earth. We generated it, and we must manage it safely and sustainably. The challenge is immense, demanding ingenuity, perseverance, and a commitment to long-term stewardship. Our future depends not on escaping our problems, but on facing them head-on with wisdom and responsibility.